We're here at Formnext at the Duet3D booth with
David Crocker,
the awesome David Crocker.
otherwise known as DC42 on the Duet3D forum.
Yeah, that's where I know you from. So I've been talking to Tony earlier. You can check that other video. But now I found where I can understand all the firmware and all the Duet technical details. They're in here. So
That's an exaggeration.
I've been just picking his brains about some parts of the firmware that I'm super interested about, like how input shaping works and how it should be implemented and why, and also about their boards, how they're better, and why all the industry uses them. So David, would you like to share with me how input shaping works and why it's important?
Well, input shaping is a technique for reducing ringing when motion systems change acceleration.
Exactly.
Every time you have an acceleration change, you get an impulse. You could smooth out with S-curve acceleration, but that's only partly effective. In fact, we did the mathematics and worked out that for typical 3D printers, S-curve acceleration wouldn't actually help because the frequencies that it cancels are higher than typical resonance frequencies in 3D printers. So that's why when Marlin was saying S-curve acceleration is a really good thing, we decided, having done the maths, well, no, we think we can do better.
Awesome.
So about, I forget if it's 2 or 3 years ago, we introduced what we called dynamic acceleration adjustments. And that, in fact, is the forerunner to input shaping. It's not as good as modern input shaping. We had it between 2 and 3 years ago, and in some systems it made a huge difference reducing the ringing. In some other situations it wasn't good enough, to be honest. So since then, of course, we've seen Clipper introduce input shaping, and that's one good thing I have to say about Clipper. They innovated input shaping, and it's well worth doing. So we looked at input shaping, we looked at the different sorts, because there are many input shaping algorithms, and we implemented it in RepRap firmware.
Awesome. What do you think about the Clipper implementation of input shaping?
The Clipper implementation is a little bit less versatile than us, but the thing to me that's odd is that they encourage you to shape the X and Y axes separately.
And you think that's not a bit...
Well, no, for 2 reasons. First of all, it isn't necessary. Because the more advanced input shapers can cancel frequencies over a range of more than 3 to 1. Now, we don't see frequencies of that range we need to compensate. Nearly every ringing frequency we see in a 3D printer is somewhere between about 35 hertz and maybe as high as 60 hertz. So you've got a 2 to 1 ratio. Now, maybe there are some printers out there where it is higher, but in those cases, I would say, check you haven't got some really loose belt or something wrong, because if you have, say, a core XY system with basically the same belt controlling X and Y, to get a 3 to 1 variation in frequencies on X and Y axes, you need a 9 to 1 variation of the masses.
Tell you what, why don't you show us on the paper?
So you can draw graphs of resonance against frequency. So that's frequency. And this is resonance reduction, where that is 1, which means no resonance reduction at all. So without input shaping, you've got that. With our original dynamic acceleration adjustment, we had a resonance reduction that was V-shaped. So at 1 frequency, you have perfect reduction, but frequencies around, it is not so good.
Yeah.
So this is usually called, in fact, that's just Z input shaping, or in fact, it's ZV. But you can then have better input shaping algorithms which use more acceleration segments. And the next one, for example, you can do looks like that, which is called ZVD, where the compensation of frequencies around the center is better.
Yeah, so you have a little more wiggle room.
That's right. And then you can go beyond that. You can do another one called ZVDD, which is even wider. And we go one higher as well. We do ZVDDD. But there are other algorithms as well. And a particularly good one is this one called EI3, And this looks something like that.
That's really
And this is, if that is F, that is 3 times F. So this one, you have compensation over a frequency range of 3 to 1. Now, with the same belt length and tensions, that means you're compensating for a mass ratio of 9 to 1, because the resonance frequency goes as the square root of mass. So if you have a Core XY machine with a head weighing, say, 1 kilogram, that would be very heavy these days, but say it was 1 kilogram, and if for some reason your gantry weighs 10 kilograms, which would be ridiculous, you've got 10 to 1 range, and maybe then this isn't good enough.
All right.
But we could always do EI4 if you really wanted us to.
All right.
But in practice, what we tend to see is the frequency ranges you get aren't anything like as high as that. So a shaper like EI3 or ZVDD can easily compensate both X and Y. Mm-hmm. So that's why you don't need 2 different frequencies. But furthermore, even if you could compensate 2 frequencies separately on X and Y, it's a bad idea.
Wow.
And the reason is, when you do corners that require shaping both axes. So suppose you have, this is an XY plane, say that's Y and that is X. So suppose you want to do a corner like that. Now, because there's a sharp corner, you will almost certainly need to slow down to the corner, probably not stop completely, but slow down and then to accelerate again here. So the way input shaping works is that the acceleration segment is split into several different segments. So
basically the last section would be deceleration and then acceleration on the other one.
So suppose we have a constant speed segment, then here we start decelerating, and here we decelerate some more, and often you have to do the same thing at both ends. So you may have...
Just to stop you here, what would happen if we didn't do all these steps?
Without the compensation, you would simply have a steady segment, then 1 deceleration segment, then 1 acceleration segment, and then steady. So this is acceleration, that's deceleration, and this is constant velocity. So that's without input shaping. Because this is a sudden change, then very likely this deceleration causes a wiggle like that, and that's when you get ringing.
That's what we want to get rid of.
That's what we want to get rid of. So that's why we split the deceleration into a number of segments, and then we split the acceleration into a number of segments as well. And typically, these segments are all the same. They're usually half the frequency, half the period of the center frequency you're trying to compensate. But for MZV, it's a bit different. Now, if you use the same input shaping on X and Y, then everything's fine because the segments on X and Y are exactly the same. But suppose you don't. Suppose you're using very different input shaping, then you may have your steady speed segment, and here we need to shape X. So we change the speed, and then here we change X again, and here we might change it again, and maybe again there, and then it's the same there. But Y, if you tune it to a different frequency, you might say, okay, it's a lower frequency we're tuned for, so we have to start this deceleration earlier. So here we'll decelerate Y, and then again there, and then again there, and then again there. But of course, these are no longer synchronized. So the path you actually get is, here's our steady speed, then we start reducing Y, so you get a little bit of kink. And then we start compensating X, so maybe it straightens out. Then we compensate Y again, you get another little kink.
Wow.
And so what happens is the tool path is no longer, even when there's no ringing, following that square path. Instead, it's following a jagged path, and your corner isn't square anymore. And the same happens on the acceleration segment. You may end up with a square there because at this point, they are both in their last segments. But then here you find that X now is accelerating more, so X goes a little bit faster than Y, then Y segment starts and it catches up again, then X, and you end up with that. And finally you end up with a constant speed segment where everything can sync again.
Wow,
so this is, of course, this is an exaggeration.
Yeah.
But that's sort of thing that's happening. So the tool path is no longer the path that your slicer is commanding the printer to do.
Yeah.
And that's
So
why...
this is sort of a trade-off, right? Like
Yes, it is.
You're compensating a little bit better potentially, but you're also potentially
You're
adding
introducing an artifact. So you're getting rid of one artifact, you're introducing another one. Now, if you set your accelerations very low, then maybe this is small enough not to matter, but you've reduced the speed again. Our view is you should keep the acceleration at the maximum you can do, but do the shaping properly. Choose a shaper like EI3, where that's your Y frequency and there's your X frequency. You can compensate both with one shaper. It does mean that you need to run the accelerometer in X and Y and then pick a curve that's going to compensate both. So it's possibly slightly more difficult to tune, but especially for an industrial customer who has to tune just once because they're making lots of the same machines, they only have to do this once. Their customers aren't going to run accelerometers except maybe as diagnostics.
So as a user, I would first run the accelerometer. I plot a graph, and that graph is gonna say, hey, our X frequency is this and our Y frequency is that.
Yes.
And
then we can show you we have a plugin for our web browser. We don't need a Raspberry Pi to run it on. It's just a plugin in our web browser that can actually show you the shape of this curve, and you can move the center frequency, and you can pick a curve that looks really good to reduce the frequencies that matter to you.
So the X and Y frequencies, even if they were to be the same, you would still need a bit of spread out cancellation, because
because when the print head is off to one side, maybe that belt length is a bit shorter and that one's a bit longer, and the frequency is slightly different.
Right.
So you still want some sort of range. So this, which is what we used to do about 3 years ago, it's not that good. You do need to smooth it out, so at least even if you don't know the exact frequency, you are covering a range fairly well.
So the smoother the better, but I'm guessing that there's some drawback for this one.
There is a trade-off, because the more you want the curve spread out, the greater the number of segments you need to split your deceleration and acceleration segments into, and because each segment is normally, for most input shapers, half the period of the center frequency you are trying to cancel, it does mean that you lengthen the acceleration.
So it takes
slightly longer. So we would say if you've got a good Core XY machine where the X and Y frequencies are really close like that, then probably just use ZVD. Or again, MZV is another good one as well.
Yeah.
Because you don't need the really wide bandwidth of an AI3. But if you've got maybe a Cartesian bed slinger where the weight of the bed is quite heavy, and when you've got a big print on it, it's even heavier, so you need that wide band. If you really want to build a big slimmer, which I know Ivan Miranda loves doing with Duet boards, I have to say, then yes, maybe then use AI3, because then you're covering a wide range. And even if you haven't measured the frequencies accurately or they drift around, it's still going to give you really good resonance reduction over a wide frequency range.
Wow. Thank you so much for the explanation. This blows my mind. This part blows my mind, because I was thinking, well, you kind of do these segments, right? I was kind of like figuring out, looking through your firmware source, and I did figure out that you're kind of like doing these little segments. But then if we were to do them independently on the two axes...
Yes. I mean, we could do that. We've considered doing it, and we have some customers who would like us to, only because Clipper does. That's the only reason. People say, Clipper does this, it must be good. Well, I'm saying it's not good. If you show me a machine where you need to compensate X and Y, and they are like 12 times apart, then either I will implement EI4 and say, use this, which to be honest would be very, very easy. Yeah. Or maybe I'll say, well, you might have a point if you don't mind the corners being not quite right. Okay, it might benefit your machine, but nobody has shown me a machine that needs separate compensation on X and Y.
Wow, I love learning all the time.
We started off selling Duet boards to the hobbyist market. And so then we just need something that works, and something was reliable enough we didn't have too many warranty returns. But right from the Duet Wi-Fi, we built a lot of resilience to the board. So there's a video I published years ago. It's not a very good video. I'm no good at making videos.
Yeah,
so I'm glad
where you're trying to destroy.
The one where I'm trying to destroy the stepper drivers, and it doesn't work.
You failed.
I failed, yes. But since then, we've had some people who accidentally put 12 volts into the 5 volt output, and we have slightly too many people doing that, so we think, what can we do? So all our Duet3 boards, if you connect 24 volts to the 5 volt output, the board will survive. If you've got anything else connected to the 5 volt output, you might blow that up, but you won't blow the board up. So we've done that. The other thing is that matters to our industrial customers, because industrial customers, they don't get the wiring wrong because they make the wiring looms and they're getting them right. And maybe they block one board in prototype, but they're getting them right. But our industrial customers have to produce machines that can be certified to CE standards and FCC standards and other worldwide standards.
Yeah, like that's a completely different world from DIY 3D printing.
Exactly.
And maybe your printer is going to burn out or something.
Burn up. And a big problem with that is electromagnetic radiation, because there are strict limits on how much radio frequency interference you are allowed to produce in both consumer equipment and commercial equipment. You're allowed to produce a little bit more, but it's still quite low, especially for CE. And that's why these days you can't make a board to someone that's easy to use for our customers to use unless you pay a lot of attention to reducing EMI. If you take any old board and you put the whole thing in a big metal box and there's no openings, yes, you can do it because the whole box is a screen. But people don't want a window so you can see what's going on inside the box. So it's important for us that the boards that we produce low EMI, low electromagnetic interference. And that means two things in particular. It means the voltage converters on the board need to be designed for low EMI. And that can get quite difficult. And we have multiple filtering and other systems on our boards to do that. And when I look at the boards from Big Tree Tech and others, in some ways those boards are quite good. They have none of this filtering. And I think it would be very difficult to make a commercial machine to pass the CE regulations with that. And the other thing that generates a lot of interference is the stepper motor outputs. And again, on the competitive boards, the boards from China, we see no filtering on those either. Wow. All our Duet3 boards, they have extra filtering components on the outputs to reduce the amount of interference they generate. Because that's important. And likewise, we make sure our CAN bus, we have filtering components on the CAN bus to make sure the CAN bus doesn't radiate as well. And all these things matter, and we do EMI testing. It's very expensive. We have to take our boards to special companies that have chambers with lots of screening in, and they can measure lots of frequencies at once. And we actually have to measure the amount of interference they generate. And it's especially difficult with Wi-Fi boards because there's another set. You have to make sure your Wi-Fi module is not generating spurious emissions. And this costs, every time we do this, it costs us well over £1,000 and often £3,000 to do a test.
Wow,
and we have to do this on every new board we produce, or every major variation we do that. And it's not cheap. And that is why we don't publish the results on our website, because then our cloners could point to the same ones. So that's one thing which isn't open source. Our test results are not open source, but to our manufacturers who buy our boards for their machines, we can produce those test results and say, this is what our board just on the bench does. And you can see as long as you use this type of cable, then even without a big metal box around it, you will meet the regulations.
Wow.
Obviously, they still have to test their whole machine because they have other components as well. But that's one thing that makes our boards different.
Wow,
This is designed for OEM customers to put in their machines and not find the electromagnetic interference too much of a problem.
This kind of technology that goes into these things, it's blowing my mind, because in our 3D printing, consumer 3D printing domain, we don't think about all these things. We're just looking into, well, that board is cheaper. Maybe I'm trying to save some money. I should buy that one. What's the difference? I mean, it might blow, it might get burned, it might destroy the printer, but I'm just gonna hope for the best. But for the industrial stuff,
Well, when we
it has to
started,
work.
when we started Duet, the company Duet3D, we started out making boards for makers, for people building machines as a hobby. But we had a 32-bit board at Duet. There was just us and there was Smoothie board, and that was all. And we said, let's make a better 32-bit board. And our boards are very popular with hobbyists and makers
Yeah,
to
'cause you
upgrade
were-
their machines. Well, now there are a lot of Chinese 32-bit boards around, and some of the designs aren't too bad. Okay, they generate too much interference, but for hobbyists, I can see the appeal.
Yeah,
They
it
are
kind
low
of
cost. If they blow a stepper driver up, they can plug a new one in.
Yeah.
And let's face it, these cheap boards, they do blow up a lot up because they don't have the protections in that we do. But the stepper driver modules don't cost too much. And I can see the appeal and see the cost is low. But for our, and some of them want to put a Raspberry Pi on it as well and run either Octoprint or Clipper. And if people who like running Raspberry Pis who love Linux, that's great. People who could program them. But we have a lot of people.
It's kind of hard to find a Raspberry Pi right now.
It is rather hard, yes. And there are a lot of people who don't want to get involved in maintaining a Linux system,
Yeah.
or who want to turn the printer on and it's ready instantly. They don't have to wait for the Raspberry Pi to boot up. They don't have to think, can I just turn this off, or do I need to shut it down because the SD card might get corrupted? And we can give you a really good web interface. We can give you conditional G-code. We can give you G-code animation. We can give you a height map viewer, all in a browser without needing a Raspberry Pi. So if you do want a Raspberry Pi, yes, we can connect one and give you even more. But we can do so much without a Raspberry Pi. And as you've said, it's so hard to find them now that we're finding I put a post on Twitter recently and said, you're having trouble finding a Raspberry Pi? You don't need one with us. You can have all these things. Input shaping, web interface, all these things. And it's been a very, very popular tweet. I've had an awful lot of likes on it.
Congratulations.
But, let's say, even when you can get a Raspberry Pi, you don't need a Raspberry Pi to do complex motion control, input shaping, up to 15 axes we support. We're about to support independent motion systems running asynchronously.
That's
You
what
don't need a Raspberry Pi for all these
I'm
things.
going to be the first beta tester for that because I really
Yes.
need it.
Because the ARM core processor on these are so powerful now. All the processors we use now, nearly all, they have built-in hardware floating point, so we don't have to worry about doing everything integer math. Our closed-loop boards, it's all floating point math. It's actually faster to use floating point than integer math these days. So, yeah, there's so much power on ARM chips. If you think you use better on a 3D printer on an 8 mega processor running 16 megahertz, an 8-bit processor, and now we're running at 300 megahertz, say, on a 32-bit processor, hardware floating point. There's so much more power. And of course, with the CAN bus, all our expansion now connects over CAN bus. So we've got processing on the expansion boards as well. And so they do the complex motion control for the driving.
I love this expansion board. It's so tiny.
Yes, to be honest, we'd like to make it even smaller. The question is, which connectors would we leave off so that it can be smaller? Because the connectors take up a lot of the space on this.
And
so
it everything that the
yes,
this accelerometer.
This drives heater, 2 temperature inputs, 2 fan outputs. One of them can be 4-wire, one can be 3-wire if you want, or they can be split 2-wire. BL touch, the motor, of course. About 3 different end-stop switches as well if you want. Filament monitor, not just a run-out sensor, filament monitor that actually compares how much movement the filament is moving with how much was commanded by the extruder.
Yeah, it's checking the actual motion.
It's checking the actual amount of motion, not just is it moving, is it not.
That's very good.
And we've always done that. So yes, we're going to make one of these that it's for small round motors. We will have to leave off a few bits for that.
Yeah.
But yeah, people want small extruders now. But we will still have the accelerometer on, of course. That's just a very small chip on it. It's very easy.
Do you think it matters to get the extruders extremely small and light?
Yes, I do.
Is there a big difference? Like
There is a
few
difference. There is a difference. I mean, one of the nice things about the Voron printer is it's not this running Clipper. I know a lot of people do run Clipper, but there's people running Vorons with Duets and wrap firmware as well. The machine is designed to be fast. So yes, you can use input shaping to remove ringing, but it doesn't have so much ringing anyway. It's designed to be able to move fast, and part of that is it has a lightweight extruder.
Yeah.
I have a Delta printer at home, and at the moment it doesn't have direct drive. So I want to put a direct drive extruder on it, and unfortunately the board's been put away. You've probably seen our smart effector, which by the way some Clipper users use, because Clipper supports our Duet3D smart effector. And we're going to combine that with this board, so it has on the accelerometer all the control, mounting holes for several other different sorts of small lightweight extruder.
Wow.
So yes, it is important to have lightweight extruders, and that's why we're moving with that. We're looking at the Bondtech LGX. I have the Mini Sherpa at home. I have an Orbiter extruder at home, and we want to have tool boards that fit very nicely with all of these extruders, and the smart effective Delta printers as well. Because I still love Delta printers, and quite a lot of other people do too.
Awesome. So you told me already that there's going to be really groundbreaking new features in your firmware, at least for my project perspective. Should we expect new hardware, other hardware stuff from
Yes,
you?
yes. I think in your other video you've looked at our closed loop hardware as well, because a lot of our customers now are building large machines. These are our OEM customers. They're making large machines, and although skipping steps may be very rare, if a print is taking 3 days and it's using 50 kilograms of material, it's quite, if a print fails after 2 days, it's expensive. So even though it may be a rare occurrence, people want to know straight away something gone wrong, so they want closed loop. And now we have, for over a year now, I think we've been shipping this closed loop board, which works with quadrature encoders built into motors, and we have quite a number of customers using that. But you've also seen we have over there our own magnetic encoder, which costs less and has higher resolution. We have the motor now with a built-in encoder, which connects just with CAN, bus, and power.
Yeah, I've seen it. It's awesome.
And we have the Renishaw linear encoder for where you actually want to measure the axis position, not just the motor position.
Wow.
So all these are coming and will be available early next year. And then separately from that, in the firmware, our next release will support multiple motion systems. So it could be 2 different heads printing 2 parts at once, although there's a patent you have to be careful of if you want to do that. But it could be you have one printing system and you have a background management system that manages tool preheating, filament movement.
Yeah, exactly the thing I need.
I don't know what people will do with it. Like when I wrote the object model and conditional G code, which I don't think Clip has anything like that yet, but it's very, very powerful. I had no idea what people would use it for. And I keep seeing new scripts people have written where they're doing amazing things that I never thought of.
Yeah.
I just thought, I think it would be a neat feature to have. I can see a few uses and maybe people find other uses. It was a very good move because there are lots of different uses people are finding for conditional G code and the object model. There's lots, yes. And one of our nice things is that because we're all open source, we have people with lots of creativity coming and doing hacks, making little changes to the firmware, writing scripts, sometimes hacking the hardware even. And then we say, hey, that's a neat feature. Let's make that standard.
Yeah, awesome.
So about 3 years ago, probably a bit longer, we decided, we realized we need to support systems with a lot more extruders, a lot more axes. We currently support up to 15 axes and about 10 extruders, 15, but we've got to increase that because one of our users wants 20 axes. So that's no problem. We'll just increase in the next firmware release.
Is that for a 3D printer?
It is for a 3D printer. Only some of the axes are actually printing, but they're using axes to do clever things as well at the same time as 3D printing. So that's why they need so many.
All right.
So we decided you can't make one board that supports 15 axes and so on. It's got to be modular, so you can have just the parts you want. And we looked for a way to interconnect the boards. And we saw some people were trying to do it with USB, but USB has very poor noise immunity. It's better than a lot of things. I2C is the worst. And when we see printers where they connect them with I2C, we think that's a very bad engineering solution. In a fixed printer where you control everything, yes, you can just about get away with it. But it's a terrible solution generally for connecting multiple parts together. So we looked to see what there is. We said, what bus is there that's highly deterministic? So when there's no errors, you know that things will arrive on time. Because with Ethernet, you get collisions and you've got to be a bit careful. If the bus gets busy, you get collisions, the throughput goes down. We said, what is also tolerant of a lot of electrical noise, because one of the problems, especially when you're running big motors, like some of our boards can support NEMA 34 motors directly, and if you put AC servos on, you get even more electrical noise. So we said, when we're connecting things together, there might be a lot of electrical noise. We want a bus that can tolerate, and we thought, where do you get a lot of electrical noise? In cars. In cars, there's all the ignition noise, there's the alternator, very noisy environments, and that's one of the reasons why doing electronics in cars is quite difficult. You have to tolerate all this noise, and CAN bus was designed to tolerate this noise. And at the same time, increasingly microcontrollers have CAN bus controllers built into them. So we looked at CAN bus, said let's use CAN bus, and our Duet Wi-Fi could support CAN. And then we started looking at it and saying, well, what messages do we need to send? How fast do they need to be? How many moves per second do we want to be able to execute? We'd like to execute 1,000 moves per second, sending all the movements over CAN bus. And when we looked at it, we found that ordinary CAN bus, you couldn't really do that. It's too slow.
Sorry to interrupt. When you say thousands of moves, are we talking about step moves or?
No, we are talking about G-code moves.
Wow.
Because if you are doing a curve like that,
it's going to be a lot.
You're printing it fast round the corner, but it's actually made in lots of small segments. That's G-code moves.
Yeah. You don't want buffers running out.
That's right. We want to send these moves over CAN rapidly. Now, you could do a bit of smoothing, and indeed for straight circles, there's a thing called arc welds to turn them into G3 moves. So in some situations you can do that, but in other situations, if it's a complicated curve, you can't do that. You've got to send these segments. So we said we want to make sure we can cope with the fastest segments that we think is reasonably likely in 3D printing. And CAN bus 2.0, because the packets are so short, you can't really do that. But there was this new version, CAN FD, where you can, because CAN FD, the packets are much longer, and you have the option to start off at one speed, and then for the bulk of the data packet, you make the speed much higher. Then you go down at the end for the CRC, so you can get a much higher throughput. And with CAN bus, we can get the packet for use. So although we often say CAN, it isn't CAN, it's CAN FD. All our Duet3 boards support CAN FD, even our little Duet3 mini board, which was meant for standalone printers. We thought, why don't we put CAN FD on that as well?
Just in case.
And it was a very wise decision, because we have people using that board with our tool boards especially, but with our other boards as well. You can have a little controller board, and then you can have a big closed loop board connected to it if you want.
This is something I love about your product line, that everything connects together seamlessly, and you don't have to configure to hack things and figure out, search on the internet, how do I do this, how do I
That's the idea.
Get these two things to talk to each other.
On this, but this is just one of our larger main boards. It's meant to connect to things like AC servos, ClearPath servos, for example. But this could be any main board. This is the CAN bus coming out of it, and it's going in this case to one of our closed loop stepper boards. So that's driving a standard motor with a quadrature encoder in closed loop mode. And then coming around here, this is an ordinary NEMA 17 motor, but we've put an encoder board on the back. It's a magnetic encoder board, which again is supported by our closed loop board. So we get very high resolution. That's 1,000 counts per rev. This is 16,000.
Wow.
So, and it costs less as well. And then this is a prototype of a collaboration we're doing with a motor manufacturer. So here we've taken our magnetic encoder, we put it in there, and our controller, and which is based on this, and we've integrated it into the motor. So we have just two cables in. This one is power, and this one is CAN bus.
Data.
And we're still talking with our customers about what size motors they want. We could do NEMA 34 very easily because this board will support high current motors and 48 volts. And we'll do a smaller, cheaper one for NEMA 17 as well.
That sounds perfect.
Yeah. And for people who want to do their own peripherals, there is a board you can get called the Sammy C21. It's a little development board about the same size as an Arduino Nano, but with an ARM chip on, CAN FD transceivers, and you can buy that from here in Germany, from Chip 45, and there's a distributor Philistruder in the USA for it as well. That will run our firmware, and you can add bits to the firmware. It's all open source like all our stuff is. So if you want a really weird sensor that we don't support, that you don't think you can connect to our board, just build it around that Chip 45 board.
So is this,
and we're doing a new one based on the Raspberry RP2040 board as well to make it even cheaper.
all right. So would this be a standalone board, or do you have to have the main Duet board?
You would still need a main board. It would just hang on the CAN bus like every other
All right.
board.
Awesome.
I think it's great that in the open source community we have three great firmwares. We have Marlin, which is the oldest one. We have RepRap firmware, and we have Clipper. And it's great that we have three different people doing three different firmwares, innovating, and we all copy things from each other. That's really, really great. I'm only sad. When we did the Duet Wi-Fi, we thought Smoothie Board is our competition. And I'm sad that Smoothie Board just doesn't seem to have gone anywhere, because I know the guys who design it, they're great guys. And I would love to have some proper competition to our boards, which at the moment we feel we don't have.
Yes. More competition is better for the consumer.
More competition, especially open source competition, is better for the consumer, yes.
And for the community.
I mean,
we are a big community.
The fact that Smoothie Board existed and Smoothie Board were talking about their version 2 board, that made us more ambitious with our Duet Wi-Fi board than we were going to be in the first place. So thank you, Smoothie Board. You made us produce a better product than we were going to.
Awesome. I keep saying awesome. All right, David. Thank you so much for all these impressive details. For people at home, if they want to learn more about your products, where could they find you?
Just go to our website, which is duet3d.com. There you will find lots of things. You will find a listing of all the different boards we have. There is a listing of all the resellers in lots of different countries where you can buy our boards. There are big customers who want lots of boards can buy directly from us too. You will find links to our wiki documentation where you will find a lot of technical details about these boards. You will find links to our GitHub repositories where all the design files for the boards and all the firmware is kept as well.
All right, we're going to add the links in the description. Until next time, be
Be awesome.
awesome.